Hey YouTube, this is version 2 of a video I previously made called Arduino versus Raspberry Pi, which is best for my kid. Making the video primarily for my wife and her students. My wife teaches science and engineering, STEM classes here in California, and she's not by her trade a scientist or an engineer. She's a journalist actually and a teacher. So she asked me to put something together that would explain the difference between some of these things. And I did that, a couple months ago and proudly posted it here on YouTube. And I tried to explain, starting from not only the hardware side, but the software side on up, what the differences between these things are. And I left the videos up there for a couple of months, I think. And one of the viewers pointed out a glaring error, and I had to pull the video down because I just couldn't leave it up with that error in there. The rest of the information I think was correct, but the one error was so glaring it was just embarrassing. So I pulled the video. I'm going to redo it here, and you can see my correction. If you had looked at my previous video, it'll explain what the correction is. I will not make the same error this time. Okay, so let's talk about Raspberry Pi versus Arduino, and what are the differences between these two things. And I'll tell you flat out right here from the beginning, the main difference between Arduino, and I'm showing you an Arduino UNO here. They come in many different form factors, and we'll go over that. The main difference between Arduino and Raspberry Pi, primary biggest difference, the big white elephant in the room, is that Raspberry Pi, and this is a version 1, there's some version 2 and other ones out there. Main difference is Raspberry Pi is a single board computer, okay? And this is a microcontroller board. Now, single board computer is really no different than any other computer you know. I mean, you are watching this video on a computer of some form. You're watching it on your laptop or a desktop machine or your iPad or your tablet or your phone, but whatever you're looking at it on is a computer, and probably more of a complete computer. If you're talking about a desktop or a laptop, you've got video output, audio output, USB input and output. You've got a network internet jack here, and RJ45. Here we have HDMI for high definition video. And here we have a bunch of what they call GPIO pins, which are used for all kinds of program-driven I/O. Much like the pins on the Arduino, you can program these things to be inputs to receive data in or shoot data out. There's a video connector on here that'll let you put some digital video directly into the machine. And then there's, this is a USB 5-volt power. And on the back, there's a place to put a SD card. And this is basically acting as your disk drive. So this is a full computer. You can hook a video monitor up to it. You can hook keyboards into it. You put your SD card in there. And you can use this just like your laptop. Now, it's going to run a bit slower than your laptop or your desktop computer. It's not made, to be to replace your high-end gaming Dell machine or something. It's made to be basically set up, put somewhere, and left there to run complicated things. But the main thing is this is a full-blown computer. It runs an operating system, and I'll explain what that is. The operating system this one runs is Debian Linux. Linux is an operating system that's been in existence for 30 years or so. It has many different flavors. There are different companies that produce Linux. Linux is also produced in an open source manner, meaning if you're a programmer, you can contribute to it. Individuals write their own device drivers. You can contribute to the kernel if you'd like. So this is a full computer, just like your Apple Macintosh, just like your Dell, just like anything, okay? Your Acer, whatever. Now, the problem is this kind of looks like that, right? And in fact, here's another Arduino that even more so looks like this because it's roughly the same size, right? And if you're not an engineer and you're not a programmer and you're not familiar with things that come naked on circuit boards, these things all look the same to you. How can you tell which is which? And I admit myself, if I didn't know what I knew, I'd be kind of confused. It kind of looks the same. Okay, let's look at this Arduino right here. This is an Arduino Due. It's got two USB B connector ports. It's got a power port. And let's see, noticeably lacking is any kind of video input and output. There's all kinds of GPIO looking IO. Now these are female connectors. This is male, but it's basically the same. I mean, you could actually plug that in. That would be meaningless, and you shouldn't do that. But just to show you that this pin form factor is the same as that, in fact. Okay, so in this case, you can program these IOs from the Arduino and plug different wires into them and different devices. But you know, that kind of looks the same. Now here's another one. Here's an older Arduino. It's not an Arduino. It's called a bare bones free Arduino. Kind of looks, not really. I mean, well, the board color is different, but I'll tell you right flat out, the color of the board is meaningless. Circuit boards come in all different colors. For instance, here's a red one, right, and a white one. The board color doesn't mean anything. So what's meaningful are the parts on the board and the I/O, the different jacks and things. So this Arduino, it's got a power. You have this pin header here, which I'll tell you flat out is meant to program it. It doesn't have a USB, so you program it through this ICSP port. And you have some I/O, but you know, I don't know, maybe it's closest to looking like that. They both have this long skinny IC on it. These have kind of these square integrated circuits. These are integrated circuits. There's some capacitors, and you know, how do you know which is which? Here, even to confuse things further, this is an Intel Edison. This Intel Edison, also, I guess it's blue. It kind of looks like that one, but not really. It's got this big square thing on it. I'll tell you right now, this also is a single board computer. Now, wait a minute. Didn't I just say a single board computer had video and audio? And this guy actually is a single board computer that talks via Wi-Fi. This little thing here is a Wi-Fi antenna. And you have a little port here where you can plug in an even more directional antenna if you want. But this is a Wi-Fi antenna. You connect to this guy via Wi-Fi, and you can do video and everything else. So, okay, how do I tell the difference between all these things? I'll tell you right now that if you know, on inspection, if you don't know the nature of the parts, you can't tell. You kind of have to look at the data sheets, and the data sheets are what the manufacturer puts out to tell you what these things do. But, you know, those of us who have been playing with these things for a long time, and in my case, most of my life, I can kind of figure out. Here's another Arduino. This is an Arduino Pro Mini. Let me take it out of the bag here so you can see it. Pro Mini. You know, this is an Arduino, and this is an Arduino. But this guy, where's all the stuff? Well, you know, it turns out that in these little holes, you can solder in these jacks. So this is a form factor that makes it really tiny, and you can put it in all sorts of things. I mean, I could put it in this coffee cup if I wanted to, right? So I got all these types of Arduinos, and I know they're Arduinos. I've got this Intel Edison, which is a single board computer, which I've told you is a single board computer. You just have to believe me for now. Raspberry Pi, which is a single board computer. And all these other things, which look radically different, but I'm telling you they're all Arduinos. Am I out of my mind? Now, one other thing that's worth mentioning, I think, is that there's a lot of software support for both the Raspberry Pi and the Arduino, and there's a lot of community support. You can find a lot of social networking, a lot of blogs, a lot of free software for both of these things, and they were both built as learning environments, learning tools. Raspberry Pi was built as a learning vehicle for students by some brilliant people in the UK, and the Arduino was developed as a learning tool by some engineers in Italy. Now, one kind of, I don't know where the name Raspberry Pi came from. It's kind of a clever name. Pi, Raspberry, yeah, I get it. Arduino was actually the name of the bar. It's a bar in Italy, I guess, that they were sitting in. drinking some wine or just talking, and when they came up with this thing. So that's where the name comes from, Arduino. It's the name of a bar. Now, another thing I'll tell you is Arduino is, this hardware is open source, and it says so right on the back here. Yeah, open source. Open source means that this is not a secret. There's nothing secret about any of this stuff on here. It uses, right now, this particular board is using an Atmel processor. It's got a bunch of very generic components on it. I will tell you that this is a crystal. These are capacitors. There's some little diodes. Here's a little LED that's lit up. These are all common parts. There's nothing that's strange or developed specifically for this thing. It's all generic stuff. Whereas the Raspberry Pi, some of it is proprietary, and you're not going to figure out what's in some of these chips. It doesn't make it any less useful. In fact, it's quite useful the way it is. And again, generic single board computer. What I wanted to mention about open source is that open source says you could, as an individual, you could take this board design, and you can get the actual layout design for this board online on Arduino.cc, and you can send away to a board manufacturer, and you can get your own boards made, and you could get these parts from DigiKey or Mouser or Farnell or Newark, anywhere, and you could make your own boards for yourself, and maybe even a couple for your friends. What you can't do is take these boards or take this design and then go make your own company and try to commercially sell these things for a profit using the name Arduino. That's not open source. That's not allowed by the license. The software in an Arduino, the software that runs the Arduino, is also open source. You can take it, you can modify it for your own use. If you want, you can contribute what you've done back to the community, and your stuff can wind up in the Arduino distribution that everybody gets, and you can enjoy the benefit of knowing that you've helped the whole community. Same with the Raspberry Pi, by the way. You can, a lot of open source on here too, but the board is not open source. What I've learned when I did my prior video is that this particular board, which says Arduino on it, is quote, a counterfeit, unquote. And what does that mean with open source? If I can take this board, if the board is public information, and I can take that design and have it manufactured myself and put this together myself, what's not right about me just making a gazillion of them and selling them to my friends? Well, that's a commercial use, and what the Arduino guys are saying is, hey, we gave this to the general public. If you want to modify it and improve it, you should also give it to the general public. Please don't take our ideas and sell them for your own profit, because we didn't do that. And that's the notion behind open source. There's a lot of open source hardware. There's a lot of open source software. The guys who contribute that expect that if you're going to use that stuff, you're not going to sell it for money. And if you do want to sell it for money, you should kick back some to them, because this is their design, and they changed the world with this. They really did. There are a lot of people who've learned about microprocessor programming who would never have done it without them. So it's only fair, I think, that if you're going to make these things, you should kick back some to them. I'm sure SparkFun does. It uses their name with their website information on there. This comes from SparkFun. And this is called an Arduino, and they don't mind calling it an Arduino, and the Arduino guys don't mind, because they get their license fee paid. This is not an Arduino. Okay, this is something that was called a Freeduino, and guys, folks that aren't paying license fees to Arduino sometimes use the Duino, D-U-I-N-O, designation to make you know that it's some kind of Arduino knockoff, and in fact it is. I mean, they've probably taken the open source, they took the open source version of the UNO board, this guy, and they made their own simpler one. Now, and then they sold these boards. They didn't actually, they just sold the board, and I bought the board from them, and I put the parts on myself. You'll see lots of things called Duino, and what that's telling you is that, yeah, it's going to work, and it's going to run, you're going to be able to use the Arduino software with it, but they didn't pay their license fees. So they're kind of, in some sense, if they're making money off of it, they're actually making money off of somebody's work without kicking back to those guys. So that's something you should keep in mind. I don't think these are available anymore, but there are lots of other things on the internet you can find called Arduino, which do probably work. They're probably ultra cheap because they get made in mass quantities, but they don't recognize the contribution that the Arduino guys made. Okay, enough of that. Okay, Arduino is a platform. Platform means there's something that's being distributed via some vehicle. The vehicle it's being distributed on is this hardware, and there's, you know, the chip, which is an AVR microcontroller that comes from Atmel. Actually, some Arduinos have different microcontrollers on them, but they started off with the AVR, and they created this board with these devices, and that's how they deliver it to you. And there's all different, you know, forms and functions of that. But the other thing that the Arduino guys did is create a software environment that allows you to program all these things in exactly the same way. Now, this is a single board computer that runs the Linux operating system. Linux is an operating system that's been around for decades, and there are all kinds of device drivers and applications that you can get for it, and you can run them on here just like you can on here. So what's the difference between this single board computer and this? You know, I've thought about this. I have recorded terabytes of video. I keep getting tongue-tied around it. Let me try it this way. Nowadays, when we talk about computer miniaturization and there being computers and everything, we're really talking about there being microcontrollers and everything. And the real difference between a single board computer and a microcontroller is how much stuff there is, because they both have their origins in exactly the same place. At the very core, there's something in here that's executing programs, and there's something in here that's executing programs. Something in here that's controlling memory. It just so happens the memory is already in there. Something in here is controlling memory. Some of it's in there. Some of it goes on the SD card over there. This has video. This does not come with video, but I can put a video processor on it. Actually, put a video a shield on there, and I can run a little device driver that talks to the video. This has a USB for keyboard and mouse. This does not. It has USB to program it only, and for power. This has HDMI. This does not. So really, the difference between a microcontroller and a microprocessor or a single board computer is that fundamental application. Typically, a computer is the end product. So your cell phone's the end product, your laptop's the end product, your desktop is the end product. You use it to do things, and you know that that's your device that you spent money for. Microcontroller sits inside some other product, and it makes it smarter. So it runs the clock on your microwave oven and takes care of the input when you press the buttons on the microwave oven. It runs your stereos so that when you are trying to run Dolby, it decodes the Dolby digital for you. You know it's in there, or maybe you don't know it's in there, but it isn't the end product. And that's the main difference between this and this. This guy is meant to be put into something and never seen again. You know, you might put this in a robot, and it might control a robot for you. Or you might put it in some other cool device. Like I put it in my Tesla coils to put music in my Tesla coils. The Tesla coils, the product, this is not. So what this does is make something smarter. Now the interesting thing is, everything I can do with this, I can do with this. And this is where the confusion comes in. Because I can take virtually any computer and turn it into a microcontroller. That would be kind of dumb because you spent a lot of money for the computer, and to make it do this, I only need like a $1 chip and about, another couple bucks worth of parts, and for $10 I got one of these versus that, which cost me, 30 something bucks. Actually, that's pretty cheap too, but your laptop costs more than $30. And to have it do what a microcontroller does is a waste of all those little doodads that are added, the nice screen and everything like that. You don't need a video screen for a microcontroller, but you might if it's controlling the video screen. So again, the difference between this and this is this guy is a much simplified version of this with all the extraneous things that you don't need taken off. If I'm going to use this to control a robot, well, I don't need a video output. If I'm going to use this in my microwave oven, I don't need HDMI. I probably don't need USB. So it strips everything out of here, gives you the absolute minimum in computing power, and allows you to program it in a very simple way so you can put it in something else. In fact, I think a good way to think of a microcontroller is like one of these wind-up music boxes. You guys have seen these perhaps. You wind them up, and it's got a little fan that spins here, which is the regulator that keeps it spinning at the correct RPM. It's got a barrel that spins, and then it's got this piece of tin or some metal with these nibs on it, these little bumps, and the bumps spin, and as it spins, the bumps pluck these different parts of this metal comb, which acts as a harp. Now, if you imagine that the location of these bumps is important to determine what song the music box plays, and of course it must be, because as it's coming through, it's plucking different notes on the thing and making a song. You could imagine having different little metal shields with these different little bumps that play different songs. I could take this same music box and put different bumps on this thing, and I'd get a different song out of it. And this thing would spin over and over and over again, and typically one of these music boxes plays the same song repetitively over and over and over again. Well, let me tell you, the Arduino does exactly the same thing. You write a program, you put it in here, and it's like your program is like the bumps on this little comb. As your program runs, the little cylinder in here spins, the imaginary cylinder is spinning, and your little bumps are plucking various, tines on its imaginary comb in here. And what it might be doing is one piece of the comb might say read an input from this pin over here. Another thing might say output a voltage on this pin over here. It might say take some data from this USB. It might say all kinds of things. But basically, what is accurate is as this little music box cylinder turns, it plays the same thing over and over again. The microcontroller does the same thing. It takes a little tiny program. It may not be that small, but typically if you're going to write a little program, you're going to write a program, and it's going to spin over and over and over again, and it's going to run the same program over and over and over and over again in something called an event loop. Now, let me not leave you with the wrong impression. Let me be accurate. I got in trouble last time for being inaccurate. Event loops are a part of software that also runs on the Raspberry Pi. Basically, any program that's waiting for input from a human being, waiting for you to type on a keyboard or hit a mouse or anything, has an event loop that runs a command, and that command says, are you asking me for anything? Are you asking me for anything? Are you asking me for anything? It does it over and over and over and over again. And when you press the key, you're basically saying, you press a key on your keyboard, you press, O, you're saying, please accept that I've given you an O. And it does whatever it's going to do with the O. It might be a command. It might just put a letter in a text file, whatever you want. Any program that's waiting for input from you is running an event loop. The difference is, in the Raspberry Pi, you can be running lots of programs simultaneously. And some of them have event loops and some don't. It's a computer. It can run all kinds of different things. The Arduino is going to run one thing and one thing alone. That little music box cylinder. Little nibs on the music box cylinder. You're going to program it, you're going to shove it in there, you're going to wind it up, and plugging it in is the same thing as winding it up, and it starts going and it starts playing the same thing over and over and over again, and that thing is an event loop. Now, if you want to program a Raspberry Pi, you can use all of the Linux tools to program Raspberry Pi. There are programs called GCC. You can use C, C++, Perl, Python, all sorts of different programming languages. Anything that's available on Linux you can run on here. So you can develop programs in all sorts of ways. There are debuggers, there are IDEs, integrated development environments, all variety of things. You can get them for anywhere. You can download them for free. The Arduino uses fundamentally one programming environment, and it's free, and it comes from Arduino. And it's the Arduino IDE. And the beauty of the Arduino, and the brilliance of the Arduino perhaps, is that all of this different hardware, and even the Intel Edison, can use the same exact programming environment to make it work. And that's kind of interesting. That's kind of like the Linux of Linux. Now, there is no Linux on here at all. But you can use this one programming environment to program all these different boards. And I'll show you how that works. So I'm going to show you how to write a program on a Raspberry Pi without using an IDE. Now you can use graphics and Windows and whatnot, but I'm going to show you using my Macintosh. So this Macintosh here is running macOS. macOS is based on Darwin, which comes from the MIT Mach kernel, which is a Linux/Unix derivative. So there's a way on the macOS I can bring up a terminal window like this, and I can write things on the command line. So what I'm going to do here is, and I'm going to go kind of fast and not explain everything, but I'm going to show you kind of how when you're a high school engineering student and you're learning how to write C programs the first time, and it's like 1986, this is the way you would do it. And I can do it this way on a Mac, and I can do it this way on the Raspberry Pi as well. Now I can't do that this way on the Arduino. We're going to do it a different way on the Arduino. So the very first program that you learn to write when you're a computer programming student or electrical engineer is something called Hello World. And Hello World, all it does is print the words Hello World on the screen. It was something that was developed by these guys who invented the C programming language, Kernighan and Ritchie, back in Bell Labs, back in the day. So what I'm going to do is I'm going to use an editor that's ancient called VI, and it's a Linux editor. It comes with all versions of Linux and Unix. I learned it on Unix way back in the day, and I'm going to write a C program and include. It's been like 20 years since I've done this, so let's see if I remember how to do it. Okay, include standard IO.H. Forget what that means. I know what that means, but that means that I'm asking this program to pull other parts of programs that it comes standard with Linux into me, and there's reasons for that. I'm going to define this as an integer output. I'm not sure why I got to do that anymore, because back in the old days we never had to define main as being an int, but you do now if you're using CC. Print F. So I'm going to print to the screen the words hello world. I'm going to type, let's see, just so you know that I did it. Let's see, make. All right, so I'm gonna print the name of my own. I'm going to say hello world, and then just so you know that I actually did it. I'm gonna just make it so that there's the name of my channel. All right. We always put a semicolon at the end of statements, and return a 0. And so this is a C program. I'm going to run the C++ compiler on it, which also handles C. And for that reason, I got to add this int. And anyway, this is a program. The main thing you got to look at here is this program. All it's doing is printing to the screen with this command printf. I'm going to print this stuff, and this is a line feed here. Dash n is a line feed. I always like to make it a line feed so that I can. I'll put a couple of them in there so that. Oh. We'll put a couple of line feeds in here so that it leaves some space on the screen. There. Actually, I'll put some line feeds in the beginning too. It's just a line feed dash n. And you're gonna have to go look at your C programming book to understand why /n is a line feed and all that. So what I'm gonna do is, all right, I wrote this little program with this editor VI. I'm gonna save that file. The file is called hello world.c. Now I'm gonna run the C compiler, CC. And the C compiler is gonna compile and link my little program here called hello world.c. And it did it just that fast. Now, I happen to know that when you run a compiler like this and you don't specify where the output goes, it always goes to something called a.out, and it has since the 1980s, and it still does it now. Okay, so I'm going to run the program a.out. In Linux or Unix. You run a program, you can just type the name of the program. I'm not sure that'll work. I don't think that works here. Nope, doesn't work. Okay, so what I'm going to do is I got to put a /a.out. And let's see what I get. So I'm gonna now I'm going to run the program A.out. So what this compiler did is it took the little code that I wrote and it made a program out of it, and the program's called A.out, and I'm going to run A.out. Now let's see what we get. Hey, look at that. So I got a bunch of spaces, and then there's my hello world, and it printed that and gave me a bunch of spaces. So that's the way I do a very simple program in Linux, and I can run that any Linux, anybody that has the C compiler, the GNU.cc compiler, I can do it. I can do that. I can write, of course, very, very complicated programs that way, but I'm just showing you that behind the scenes, the IDEs, the integrated development environments, have this kind of thing going on. Okay, so now that I've shown you how to do a command line program. Command line meaning I don't have a mouse here. I brought up a terminal window on the Macintosh, Mac OS, running the terminal program. You can do the same thing on Windows. Bring up a terminal window. You can type to MS-DOS. You can do, and certainly the same thing on Linux. You can't do it. Actually, you can do it on your iPad for certain commands. There are apps that let you bring up a terminal window. Kind of hard to do because you're typing on the iPad or the tablet screen. But there are apps that let you bring up a terminal window, and this is the old style way of doing things. All right, so and I'll do this first, and then I'll show you how to do it with something called an IDE. And what we're going to do is we're going to write a program. We're going to write that hello world program here on the Intel Edison. Now here's the Edison. It's plugged in. It's plugged into 2 USB ports. All these USBs are doing right now, as far as I'm concerned, is they're providing power, right? USB provides power and communications, but in this case, I'm just using it for the power. There's 2 boards. There's the Intel Edison itself is on this little tiny square board, and then there's a bigger, slightly bigger board, which has the USB hardware on it in this case. And all it's doing is one of these USBs is powering this board, one is powering that board. That's it. And what we're going to do here is we're going to talk to the Edison via Wi-Fi. So here's a little Wi-Fi antenna here. I'm not using these USBs to communicate. It's just the Wi-Fi through my house network. So I'm going to put this down, but you have to trust me that this is what we're going to be talking to. We're not going to be communicating to this big computer here. We're going to be communicating to this little computer through the bigger computer. Okay, and so I'll put that aside. Now what I'm going to do is I'm going to run a program called SSH. And what SSH is an old style secure communication program that lets 2 computers talk to each other. And basically, when I say talk to each other, I mean I can type here and it winds up on the other computer. Now what I do is I type the SSH command in the terminal window. I say -L. I tell it what user I am. I'm user Joe. I know there's a user account called Joe set up on that Intel Edison because I just did it. And I also know what the IP address is of the Intel Edison because I also set that up previously. And you got to know the IP address. Every computer has an IP address in your home. In your home network, they will tend to have addresses that look like this. And I don't want to get into the whole rigmarole of how IP addresses are assigned and whatnot. We can talk about that in a different video. But the IP address is the number that I'm going to use that says this is my Intel Edison. I know my Intel Edison on my home network is 192.168.0.20. And I'm going to log into that with a user called Joe, which is me. And it's asked for my password. Okay. I'll set my password. And there we go. Now I'm talking to the Edison. I can do an ls, which in Linux says give me the directory listing of what's there. Actually, there's nothing there. I got nothing in my directory. I got no files. I can say ls/. This is all Linux rigmarole, and what this is showing you is that at the very high level, I've got all these different files at the on the Edison itself. There's a non-volatile memory in the Edison. It comes with it. I forget how big it is. I think might be gigabyte. In any case, in my home directory, in my home file, which is like my desktop, this is my desktop, I got nothing. I type ls, which is the little, show me what files I got on my desktop, I got nothing. All right, now I'm going to create a file just like I did on the Macintosh with the vi editor command called hello world.c, because I'm going to use the C programming language, okay? And I'm going to do my include, and then I'm going to do my int main, and that's the main part of my program. And we'll put the close bracket there. And all we're going to do, just like we did before, is I'm going to print the following. I'm going to do a bunch of line feeds. I'm going to say hello world, and then I'm going to put some stars. I'm going to put the name of my channel. And some more stars, just for the hell of, oop, got a mistake there. Another star. And a couple more of these line feeds. And close quote. And we need that. And return 0. Because all good Linux programs return 0 if they worked. And I don't anticipate this is not going to work. Okay, now I'm going to save that file. Now if I do an ls, what we will see here is that I've got a file, you can kind of see it there, called hello world.c. It's right there. Okay. Now what I'm going to do is I'm going to compile and link that program with the GCC compiler that comes with every Linux system. Compiling means I'm going to turn those words. So there's the words I typed, those things. That's a program. It's going to turn those characters into instructions, little low-level binary bits that the computer can actually execute. Computer can't execute these words. It's got to execute its own little machine language. You can Google or go to Wikipedia, look up machine language, look up compilers. It'll tell you what it does. The main purpose of me showing you this here is to show you that the Intel Edison is a real Linux machine. And it's running Yocto Linux, and it has a GCC compiler along with it, like all Linux machines do. So again, all this is happening on this little guy here. All right, it's not this. My Macintosh is just being used as a dumb way to get into that thing via the Wi-Fi. So in order to compile it, hello world.c. What I'm going to do is I just type the cc command and I compile hello world.c. Now it compiles, it turns it into machine code. It also does something called linking. You can look up what a linker does. Linking says when I type these things, like for instance this printf is actually another program that somebody else wrote that comes with Linux. Linux is written in C and blah, 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 and those things are in libraries, and the linking says Joe didn't write printf. Printf was written by whoever supplied GCC, and that's a program, and go get that program and put the machine code for that program, and all we know is that Joe wants that little program to write hello world on the screen. So we compile it, our little stuff, we link it with other code that comes with Linux, and we do that in one step by typing cc. Beak. Oh, what did I do? Incompatible and plus C. Now this is typically what happens here. Okay, and I know I got an error. Do you know why I got an error? You might see it if you know something about programming. You might see it. Let's. I got to go back into the VI editor here. I'm gonna. I didn't write the word include. I said include. I-N-C-L-U. This has got to be the word include. D-E. Include. Okay, and so what you see is I got a compiler error. It can't do it because, and it gave me this really weird, this is part of programming on Linux. In general, you got to figure out what all these things mean, and it says, let's forget about what it says. All it says it didn't work. Now I'm going to try it again. Okay, let's go this time. So I'm going to say cc hello world.c. Try that again, and see, it works. Nothing, and I know it works because nothing happened, right? It didn't give me, it didn't complain to me. It just came back and said, all right, what else do you want to do? Now I happen to know that on a Linux machine, when you compile and link a program, and you don't tell it what the name of the output file should be, it puts it into a little file called a.out. And if I do a ls and I say, show me what's on my desktop, aha, now I got a program called a.out. I didn't write that program. The compiler created it. A.out itself is a program, and we can run programs on Linux by just typing their names. So I can type a dot out. Oh, doesn't work here. Okay, so what I got to do then is I got to type a dot slash a dot out, and then I get to just run. That's how I run a program on Linux. On most of your Windows-based machines, you double-click a program and it runs. And Linux, this is the old way to do it. You just type dot slash a dot out, and then if I do that, look what it does. It prints the characters here. I'll just lower that a little bit so you can see it better. It printed what I told it to print. Hello world, music. I'll do it again. I'll run it again. In fact, I could run it a gazillion times, and all it's going to do is print what I told it to print. So, again, you have to believe me. That's happening on this little guy here, talking to the Wi-Fi to the internet in my house. Okay, because we're gluttons for punishment on this channel, I'm going to show you how to write the same program on the Intel Edison using an IDE. Now, an IDE is a Windows-based way to write a program and compile it, and all the little doodads and things you have to do behind the scenes to write a complicated program are taken care of for you. Now, this little one I did here was so simple. I just typed CC, but trust me, if you're doing more complicated programs, you may only have to type the CC command, but you may have to do something called a make file, and you have to put different files together, and it gets pretty complex. So then IDE handles that for you. Now, I'm using the Eclipse IDE. Eclipse is an application that runs on all different platforms. It's written in Java. It's supported by a community. And what you'll find with Eclipse is that it'll run on Mac, it'll run on Windows, it'll run on a Linux machine. Anywhere Java runs, it'll probably run on I wouldn't doubt that there's a version of Eclipse that runs on tablets. I doubt there's any that runs on phones because the phone manufacturers want you to use their emulators and whatnot. Anyway, let's not get into that. That's kind of complicated. But it runs on any laptop or desktop machine you can get an Eclipse for. So this version of Eclipse came for the Intel Edison, and I got it off the Intel website. There's a version that runs on the Raspberry Pi, and I'll see if I can start that right there and show you that in a sec. The Eclipse, it tries to be all things to all people, so it's got a huge, rich command set, and I'll tell you, it's really not difficult to learn, but there's a lot to remember. So if you're a kid trying to learn this stuff, you may do well trying to learn Eclipse, but boy, I'll tell you that it's a non-trivial thing to pick up. Now, this version of Eclipse, I previously have a program in there, a project I did that I showed in a previous video. What I'm going to do is I'm going to open a new project. I'll go over here, new project, okay. And I'm going to open up a new project, and it's going to be an Intel IDE Developer Kit project, and because it's going on the Intel Edison, and it's going to be a regular old C program. Look at all the commands I'm having to type, and I'm going to call this new project Edison Hello World. That's it, Edison Hello World. Okay, so I have to open up a project for this, and da-da-da-da-da-da. Okay, so look at all the cool things that have happened now. Now, all I did, I opened a project, and it gave me a little C program here. And it automatically wrote things that I wrote before. You saw me write, include standard.io.h. It's also included this other thing here for me. It wrote down the main, created this main with the open bracket and close bracket. And it's also put this loop. This is a for loop. And trust me, this would be like that music box kind of loopy thing. It's just going to iterate over and over and over again whatever you put in there. So it's trying to emulate the microcontroller side of things. I'm just to make it similar to what we did before. I'm going to take this stuff out. Okay, so I'm going to put in what I put in before. So this is going to look exactly like what I typed before, right? So printf. Oh, not printf. And now you'll notice I'm just typing, for instance, I type one quote here and it gives me two. I type one open bracket, it automatically closes the bracket for me. So that's kind of cool. Hello world from music, lightning, and then a couple more line feeds. And then if I hit tab, it'll go to the end. And that's the beauty of Eclipse. All I've had to do is didn't have to type every single character. It actually will complete some characters for me. You'll notice some of these words are different colors. This nice little magenta thing says it knows that this word include is a C programming keyword. For instance, if I misspell that like I did before, notice it turns black. So it's saying, wait a minute, I don't know what that is. And it puts this little question mark here. And it says, if you can see invalid preprocessor directive. Okay. That's a complicated way to say that I misspelled it. And all right, so there we got basically the same program. And if I get rid of this comment here, it'll look exactly like the other one. Gets rid of these spaces. All right, that should look familiar. Actually, I don't even think I need this other include, but I'm going to leave it in there. Anyway, so now, in order to run this program, I don't have to do anything but click this little arrow. What this little arrow is going to do is it's going to compile and link that program, and it's going to put it on this Intel Edison. So it's going to compile it on the Macintosh, and it's going to shove it into my little Edison, which is over here on the side. Trust me, I haven't disconnected it. It's still sitting there. And it's going to connect it through the network to this IP address over here, and you saw me SSH to that IP address before. So I'm going to click that, and when I come down here, all kinds of things are happening, right? It's doing all kinds of stuff. It's who knows what it's doing. It's blah, blah, blah. It's linking, it's compiling, it's connecting, it's looking for libraries called MRAA, UPM. And then it asked me if I wanted to save it. Yes, and so it's built it. Now it's logging into the Edison, and it shoved that program in there, and it ran it, and it logged out. Okay, so here it is. Hello, world from Music Make Lightning. So all that to do this printf. Now, I assure you, the cool thing is I could have left that loop. That could have been looping forever. In fact, why don't I put that back in there? I'm going to put it in there, and then you'll see. Put the for loop back in there. For yep, only need 2, and then I'm going to open bracket, and then on the other side of this I'm going to close the bracket. And now what you're going to see is that it's going to keep printing that pretty much forever. I'm going to get a lot of those. So I hit compile, and I'm going to save those changes. And bidding, it's built it, and now it's logging in. And there we go. See, it's just over and over and over again writing the same thing. That's kind of cool. I can actually stop that program by hitting that little stop button, and it will stop it for me. Okay, so there I've created and run the same program using this nice little IDE environment. Okay, and just one last word. You'll just have to trust me that if I was to do the same thing on this Raspberry Pi, it would look the same way as it did on the Intel Edison. I could run Eclipse actually on the Raspberry Pi, and instead of running it here on the Macintosh, I could actually run Eclipse on the Edison, but I didn't want all that traffic on the network. I could run it from a command line, definitely. And the main reason I'm not going to do it is that this particular Raspberry Pi doesn't have Wi-Fi on it. I would have to use the hardware. I'd have to connect it to my home internet via the RJ45 with an Ethernet cable. And I happen to know, and I have this little operating system plugged in there. I got Debian Linux on this SD card, and it would start up and it would run. It would look just like the Edison. But again, the thing is, I know that the internet, this has a hardwired internet address on it, the way I programmed it. I've already got another Raspberry Pi in my house, and what it's doing, and I can show you that here if I go to the my browser, and it is actually serving up a weather channel. So this comes from a Raspberry Pi that's in my living room, and it's talking to a weather station. And so it's a Raspberry Pi, looks just like this one, and it's running number of programs simultaneously. One of them is pulling data off of a Davis weather station, and another one is creating a web server, and another one is putting this web page onto the web server, and it's running all those programs simultaneously, and it gives me this nice web-based way to look up what the weather is at my house using a program called WView. So that's an example of what you can do with a single board computer where you're running a whole bunch of different programs at the same time. Now, that's very, very different from the microcontroller side of things. Now, the next thing I'm going to do is I'm going to bring up the Arduino IDE. All right, so I just did that. In fact, you can see over here in the little menu, I've got the Arduino IDE talking to me right there. I clicked that, and I've got this window that popped up. Let's put it in the center of the frame. And what I'm going to do is I'm going to run the equivalent of that little hello program. And that little hello program on an Arduino, the guys made it, what it does is it blinks a little light here. So again, the microcontroller, I've got no video output on this thing. All I'm going to do is I'm going to control this little light, and I'm going to control it repeatedly, just like the music box example, right? So what I'm going to do is I'm going to write a little program, and the program's going to loop over and over and over and over and over again, just like the music box. And as it loops, it's going to do what I tell it to do. And what I'm going to tell it to do is this. So again, here is programming language. It looks like C. It looks like Java, looks like a whole lot of programming languages these days. And I'm not going to go into how you write code. You'll have to look that up yourself, but this is a very simplified sort of C thing. What I'm going to do is I'm going to say that pin 13, LED pin 13, I'm going to define this variable LED pin to be number 13. Now, if I look at my Arduino here, I don't know if you can see this, but there's a little pin 13 right there. This is pin 13. And I happen to know, and why do I know this? Because I read the Arduino documentation. That pin 13 is connected to that little LED right there. And I can also look at the board and see where the trace goes, and I can see that the copper trace goes from there to there if I look really closely at the board. But I read the documentation, and almost all Arduinos and everything that claims to be like an Arduino connects pin 13 to an LED. You can disconnect it if you want, but it kind of comes like that by default. That's part of the open source. So what I'm going to do now is I've got this board plugged into the USB, right? Plugged into the USB right there. And what happens then is I'm going to upload a program into here. Now, how does that work? The way it works is this. There's some memory inside this little microcontroller chip. This microcontroller chip is your music box, and there's memory in there, and part of that memory represents the little drum that spins around and around and around and plays the music. Another part of the memory is something different, and that different thing is called the bootloader. Now, the memory in this chip stays in the stuff you put in memory stays there until you rewrite it. So in fact, even if I take the power off, the memory is still good in there. And there's a little program in there called the bootloader. And what the bootloader does is when I power it up like I just did, the bootloader says, hey, are you trying to stuff a program in me? If so, I'm gonna put myself into a mode where I allow you to reprogram the little cylindrical music box thing. And if you're not trying to load a program into me, what I'm going to do is I'm just going to play a little music box thing, right? So the bootloader is sitting there staring at me and waiting for me to do something. And in fact, I can trigger the bootloader every time I initialize this thing. And I initialize it either by, I plug it in. You can see this little light flash there. The light's flashing because the bootloader is running. Let's see if you can see that guy right there by my thumb. Right? He's flashing because the bootloader is running. Bootloader is asking, are you shoving a program into me? Yes. Then I'm going to let you have access to the little cylindrical music box thingy, and I'll let you put a program in there. If the answer is no, I'm just going to play the little music box thingy. Now, right now, the little music box thingy is doing I don't know what, because I haven't programmed this thing yet. It's doing nothing, probably. The other way I can initialize it is by pushing this reset button. See, if I push the reset button, that light flashes. See that light flashing right there? I push reset. Light flashes. That means the bootloader is running. Now, I don't have to unplug it and replug it in to get the bootloader to run. In fact, the Arduino IDE will send a little a little reset signal through this and get the bootloader to run. So what I'm going to do here is set up the IDE to look for this Arduino UNO board. So what we'll do is we come up here, and where it says Tools, I say, what board do I have? Well, I've got an Arduino UNO. Look at all the different types of Arduino boards, by the way. And in addition, I can program the Intel, in addition, I can program the Intel Edison or the Red Bear Labs boards or the BLE Nano boards. I'm not gonna mess with those right now. I'm gonna go back up here to UNO, and I'm gonna tell the Arduino programming environment that I'm connected to this port, that the Arduino is talking to me to this port. Now that you see there's 3 ports here. One, it's looking for Bluetooth. This particular computer has a Bluetooth on it. I don't have anything plugged into Bluetooth. It's got an RS422 controller for video. I don't have that plugged in either. But I do have this plugged in. And what it's saying is those ports are sitting there waiting for me to do something. I'm not doing anything to it. I just know that the only USB legal thing is this right here. And you can see it says USB modem. So I'm going to tell it my Arduino is plugged in there. Okay. Now I'm going to run this program. This program is going to take pin LED 13. It's going to say that it's an output pin, that pin 13 is looking for something to come out onto it, some voltage. I'm going to take that voltage and I'm going to turn it high. I'm going to write a high voltage to it. That's the way you do it. Just like I wrote hello world to the screen here, I'm going to write a voltage because it's a microcontroller. Microcontrollers can write voltage. I'm going to write a voltage to LED pin, which is number 13. I turn it high, and then I'm going to wait. This is a delay, and delay tells me to wait, and I'm going to wait 100. 100 is 100 milliseconds. A millisecond is 1,000th of a second. So I'm going to wait for 1/10 of a second, and then I'm going to write a low voltage with 0 volts. I'm going to write 0 volts to pin 13, and then I'm going to wait a half a second. And then, because this is a little music box cylinder, I'm going to go back up here again. I'm going to do the same thing over and over. And by the way, this says loop right here. And it says loop for a reason, because it's going to loop over and over and over again, like the music box. So if this program works and gets in there, we're going to see this light flash. It's going to be on for 1/10 of a second and off for half a second. I purposely did that so that it would be asymmetrical, so that you'll be able to tell that, you know, it's not some other kind of thing that's happening. All right, so here we go. I'm going to press that. The program compiles, runs, flash. And now you saw a whole bunch of flickering. That was when the IDE hit the reset button. The bootloader allowed me access to the little music box piece. That program got shoved in, and as you can see, this light is flashing. I hope you can see that. Yeah. Off for 1/10 of a second, on for half a or off for half a second, on for 1/10 of a second. And just to show you that we're not lying here, I'll do the opposite. I'll turn it on for half a second and off for 1/10 of a second, just by simply doing that, changing those variables. So turn it on, wait half a second, turn it off, wait 1/10 of a second. Let's shove that in there. And now you see it's mostly on. Okay, so that's how easily that worked. Now let's try this with one of the other Arduinos. Okay, now I'm going to do the same thing with this Arduino Due as I did with the UNO. All right, Due is obviously a different form factor, a bigger board. It's got a bigger processor. I think it's faster. It's got more memory. I can put bigger programs in it. Lots more I/O. It's got software USB as opposed to the hardware USB, so I can play around with the USB on this one like I couldn't on the other one. And I have to use a USB-B micro here, and hopefully you can see those lights. Okay, so that power light's on. All right, now I'm going to come back here, and I'm going to use the exact same program, not changing the program at all. I'm going to come here to Tools. I'm going to say that I'm on an Arduino Due, which is this guy down here, and the Arduino Due's got 2 USBs. This one on this one. I'm telling it I'm programming it on the programming port. Why not? And I'm also going to come here on Tools, and it says here Arduino Due programming port. That's what I'm doing. All right, so I've selected the board, and I've selected the USB. And now what I'm going to do is I'm going to load this program. Now, remember what this program did before I switched over. It's on for half a second, off for 1/10 of a second, and we're going to specifically look at the L the LED that's got the L next to it, and it's that one right above the little green one that's on right now, right? So let's see what happens. I'm going to program it. So program's being compiled, program's being shoved in there, lots of other stuff's being shoved in there along with it, and now you can see the L is flashing, right? Can you see that? Yeah, it's on. Most of the time it's only off for 1/10 of a second. What I'm going to do is here, what I'll do is I'll turn it off and on for the same length of time. It'll be on 1/2 a second, off 1/2 a second. Let's see that happen. Program's getting shoved in there. You see all these lights flashing. And there it is, off, on. Now you can clearly see it's on and off for the same length of time. So I am programming it here. Now, what's all the stuff that's getting shoved in there? The stuff that's getting shoved in there is kind of like the operating system. It's not an operating system, but more or less it controls all this hardware for you so that you don't have to. So it's like an operating system in that sense. The Arduino core, this IDE controls the Arduino core, and the core is in a sense the operating system for these things. But it's not a multi-processing operating system. It doesn't let you run more than one program at a time. It doesn't have native video in it. You can get all kinds of I/O output for this. You can actually get little screens for it and everything like that. But basically, the low-level operating system doesn't know anything about that stuff. Okay. Okay, now I'm going to show you how we're going to program this little Arduino thingy. It does not have a USB, as you can see. In fact, you can get an outboard little USB board you can plug in and you can wire it up. But I'm going to do it with this. This is an ISP, in-circuit programmer, that comes from AVR, and you can buy these online. This is an AVR ISP, and it has this little plug that plugs in right here to this connector. Let's see if I can take it off there. There we go. You see there's a connector right there. And this guy plugs in right there like that. And you see the little light turns green on this. And I'm plugging this into the USB for the machine. Now, I've got to use a little breadboard and stuff because the LED on here is not connected to pin 13. It just tells you there's power. So I've got this little outboard LED and this resistor, and I'm going to actually connect the LED to pin 8. So if we go back up here to our IDE, and what I've done is I've changed the LED pin to pin 8, right? And what I'm going to do is I'm going to turn it on for 1/2 a second and off for 1/2 a second. All right, so I'm going to put voltage on pin 8 for 1/2 a second and turn it off for 1/2 a second. Now I've got to do something slightly different up here in the tools section. So first thing I got to do is I got to figure out what type of board is this, because there is no free Arduino board, because these guys have not paid any homage to the Arduino guys. They haven't paid their license fees. They're not open source guys. I don't know where I got this board. It came from somewhere. But there is, and when you get something like that, you've got to just, it's trial and error. One of these things will probably work. In this case, I've been able to select Arduino NG or older, and I know the chip on it is an 18 mega 168 because I can look at the chip and it says 168. But port-wise, I don't have a USB port here. What I've got to do is I've got to go to where it says programmer, and I've got to select the AVR ISP. Now you can see there's all different ways, all different types of programmers you can choose. USB Tiny, actually Adafruit has one of those. There's all these things. You can actually use another Arduino to program it. I'm going to use this AVR ISP because I haven't had it laying around for a few years. Now the different thing you've got to do is when you want to upload to the board, you can't just type upload. You've got to say upload using programmer. All right, so I'm going to select that, but first I'm going to take you down here and get that in focus, and I'm going to show you what happens when I select upload using programmer. So I selected that. Light turns to orange, and now you see I'm flashing on for 1/2 a second, off for 1/2 a second. Okay, so that's another way that you do this when you're basically in a situation where you don't have a USB, you got a board without a USB, and you're just programming the chip in a naked way. Now another thing I could be doing here is I could set up suppose the chip itself was brand new. I can go online, I can order these chips and just plug new ones in. If I was doing that, I'd have to put a bootloader on it. And so what you can do is you can come up here to the menu. You can't just plug the chip in and start programming it. You've got to burn a bootloader on it. And there's an item that you can select here and say burn bootloader. So you do that first. You got to use the ISP to do that. The USB, you can't do it with a USB. I don't think you can anyway. You got to use the ISP, and you burn a bootloader onto the chip, and then you can program it. And the final thing I want to show you here is how I program this Intel Edison so that, and an Intel Edison, again, a single board computer, but in this configuration, it's actually acting like an Arduino. This is the Intel Edison here, and it's on this big board. And this board is basically a mock-up of the Arduino, all the Arduino hardware IOs. So what happens here is when you fire up the Edison, what it's going to do is it's going to go into a mode in Linux where it thinks, it fakes out the Arduino code into thinking it's in a microcontroller instead of in a Linux machine, and then it uses all this other hardware to mimic the I/O on the Arduino. In fact, if I look at the Arduino UNO here, look at the black ports, input-output ports, same as here. So this has got the same I/O as a hardware I/O here as an Arduino UNO, except I've got, I still have I have a USB power. I got 2 other USBs here. I can put an SD card in there, so I can do a lot of things pretty flexibly. So what I'm going to do, right, and I got the same program I've put into all that other stuff, right? Same exact little blinky program, just blink a light on pin 13. Actually, I got pin 8 selected here. Let me put that back to pin 13. All right, and I'm going to try to blink a light on this. Now what I got to do is I've got to go up here. I've got to select Intel Edison. For the port, I selected USB modem 323. I've had to connect 2 USBs to this thing. One is for power and one is the actual communication. And now what I'm going to do is I got the same old program I had before. I'm just going to upload it into here. Push that button. So it's compiling. Let's see if I can get both of these things in the camera at once. It's compiling, and transfer is complete. And now we see an LED blinking there. Blink, blink, blink. Just to prove that it's my LED that's blinking, and it's my program that's blinking it, I'll change the timing. Okay, so I'll have it on for ½ a second and off for 1.2 seconds. How about that? That's what I typed in there. All right, we'll upload that. So on for ½ a second, up for 1.2 seconds. Yep. Actually, I'll make it even more severe. Well, I would off for 2 seconds. Off for 2 seconds, on for ½ a second. How about that? This thing goes so fast it's hard to tell. Off for 2 seconds, on for ½ a second. All right, so you get the idea that I'm actually programming this thing like an Arduino. Again, this is a single board computer running Yocto Linux. So it is running Linux. But we've got a little program running in this that makes it look like an embedded controller, a microcontroller. And so when the Arduino software comes into it, it thinks that it's sitting in a regular old Arduino just like this, and it does everything the same way that it usually does, and all this hardware mimics this hardware over here. Okay, let's try to wrap this thing up. We started off trying to tell the difference between a Raspberry Pi and an Arduino. We talked about the differences between a single board computer and a microcontroller. I showed how the Intel Edison is also a single board computer. The Intel Edison runs Linux. The Arduino, the Raspberry Pi runs Linux. And I showed you how you could write a program in Linux using the command line. I also showed you how you could write a program in Linux using the Eclipse IDE. Then we talked about the Arduino style microcontrollers in general. And we talked about all the different types of Arduinos we could have. We talked about Freeduinos. We even discussed how to program a Freeduino using these little 6 pins here, which are the ICSP pins. which appear even in a regular Arduino UNO has ICSP pins. Actually, you could program that with the in-circuit programmer as well. So we showed how you could do things with in-circuit programmer. We showed how the different Arduinos will run the same code using the same IDE. We also showed, perhaps even kind of indirectly, but something you should note is that when we talked about microcontrollers versus single board versus computers, and how the computer is the end product and the microcontroller is embedded in the end product, we said that, in fact, microcontroller is kind of a really simplified version of the computer. They can do some of the things the computer can do, but because a lot of the functions are stripped off and it's a simpler computer, it does a much more simpler task and it gets embedded in another product. I even showed how in the case of the Intel Edison, you've got a single board computer, which we were running programs on and watching that go, but we also have a dumbed down version, which happens to be a lot bigger, that turns the Edison into a microcontroller. And that's a classic example. I can turn any computer, just about any computer, into a microcontroller, but I can't turn a microcontroller into a computer that easily. And hopefully that clarifies this mess. I really want to thank you guys for patronizing the channel. This has been a long video. It's taken me 4 or 5 days to make. It's taken me another day or two to edit. I hope to edit it in a way that makes it more viewable. I really appreciate your patronage. I really appreciate you coming to the channel and subscribing, and I appreciate the comments. Keep them coming in. If I'm saying anything inaccurate, I will try to fix it. I am not interested in spreading junk on the internet. I want to put real data that people can use, especially the people that know me. And if you don't know me, well, I want you to be able to use good data too. In any case, I'm Joe. Thank you very much for coming to the channel. Thanks for subscribing. Thanks for the comments. See you next time.